Hello, this is Mrs. Nearing, and we're going to talk through some notes related to periodic trends. We are in Unit 1, and we're in Part 3 of Unit 1. So we covered calculations involving the mole. Then our next topic was atomic structure. We got into electron configurations. And in Topic 3, we're going to be covering periodic trends. And if you wonder what periodic trends involves, there's some terms we're going to need to know, such as atomic radius, ionization energy, ionic radius. And our goal is to use Coulombs Law, which we've heard of before, and something called effective nuclear charge, which will be something new, to predict and explain periodic trends. An example of a question you might get would be to compare and contrast two elements. For example, which element would have the larger first ionization energy, silicon or sulfur, and why? So that's the type of question you want to be able to answer. First of all, to review Coulombs Law, we've seen this before. F is the attractive force between particles of opposite charges. So when particles have the opposite charge, they will attract. If they had the like charge, they will repel. So two electrons would repel each other, but an electron and a proton will attract each other. The Q represents the charge magnitudes, and one of those Q values will always be -1. That's the charge of one electron. And one of those Q values is going to represent what we call the effective nuclear charge. And when we think of it that way, then our F force will tell us the attraction between one electron and the nucleus. And then R is the distance between the charged particles. We have seen that R is directly related to the shell number that the electron is located in. The effective nuclear charge. So what is that? That is the average or the net charge felt by an electron. And it's the net effect of its attraction to the protons in the nucleus and the repulsion from other electrons. Here is a visual representing that. You can see right here we have a valence electron in the 2s subshell. It is attracted to the 3 protons in the nucleus, but it is also repelled by those 2 electrons that are in the core, that are between it and the nucleus. So we can think of the effective nuclear charge as essentially being the net charge, considering both the attractive force and repulsion force. And if you look up here, here's an equation that represents the effective nuclear charge. To find the effective nuclear charge, you take the actual charge of the nucleus, that is your number of protons, and subtract from it what we call the screening factor. It's the charge screened by the other electrons. You will also hear this referred to as shielding, and that's basically screening or shielding represents a repulsive force. So we're looking at the net effect of the amount of protons attracting that electron to the nucleus and the amount of other core electrons shielding or repelling that electron. Core electrons are the ones that do the effective shielding. Valence electrons, you'll see some shielding effect from valence electrons, but not really. We tend to ignore that. So a simplification, as shown here in this example with lithium, a way to simplify our effective nuclear charge calculation is to say the effective nuclear charge is the number of protons minus the number of core electrons. So you can see in this example with lithium, we've got 3 protons and there are 2 core electrons, so we say the effective nuclear charge is +1. So now you want to take a moment and do this with the elements carbon and oxygen. Checking your work here, it should look like this. So we've got our electron configurations. You'll notice carbon has 6 protons, oxygen has 8. Carbon has 2 core electrons, oxygen also has 2 core electrons. So the effective nuclear charge of carbon is 4, while the effective nuclear charge of oxygen is 6. You'll notice as you look on a periodic table, oxygen is to the right of carbon, and you will see that as you go across the row from left to right, the number of protons increases as the atomic number increases, but the number of core electrons stays the same. And that's because as you go from left to right on the periodic table, those all have, every element in a row has its valence electrons in the same shell. So like the second row has all second shell valence, third row is third shell valence, fourth row is fourth shell valence. So protons are increasing, but core electrons stay the same, so the shielding is basically staying the same. That means overall your effective nuclear charge is going to increase. Here's a visual showing what we were just talking about here with carbon on the left and oxygen on your right. You can see oxygen has a more positive nucleus, same number of electrons shielding, so it overall has a greater net charge felt by those valence electrons. So we say it has a greater effective nuclear charge. That means oxygen's valence electrons are more attracted to the nucleus than carbon's valence electrons are. Looking at fluorine and chlorine, these are elements that are in the same column as each other. And if we look at their electron configurations, chlorine has more protons than fluorine, but it also has more core electrons. So when we look at the effective nuclear charge, they have effective nuclear charges that are the same. They're both 7. So as you go down a column from top to bottom, the numbers of protons is increasing, but the number of core electrons is also increasing. So the effective nuclear charge is staying roughly the same. Okay, so defining some terms, atomic radius defines the radius of an atom, and we define it by it's half of the distance between nuclei of two like atoms. And there's a picture here. This is from your textbook. And we often see this measured in picometers. If you're curious what a picometer is relative to a meter, it is very small. Here we can see the trends in atomic radius. And you can see as you go from left to right, the atomic radius is in general decreasing. And as you go from top to bottom, the atomic radius is increasing. And these values, I believe, are in picometers. Yep. Okay, ionization energy is the energy required to remove an electron from an atom, so to form a positive ion. And we've got a visual and an equation that shows what that would look like. Here we can see trends in first ionization energy. We can see as we go across a row from left to right, the ionization energy increases. And as we go down a column from top to bottom, the ionization energy decreases. And in your text, it goes into explanation about why we see these trends, and we will talk about this more in class next week.